so you've seen Chow Ma talk about reduction of spurious. You've seen Yang Li talking about elimination of internal multiples in a 1D Earth. So please understand, as Yang Li mentioned, it's a reverse engineering problem. Because for a 1D Earth, you can analytically see how the amplitude is created, and you can see how the event at depth is a combination of reflection and transmission coefficients. As soon as you're in multi-D, all of that, you have a curved boundary. Yes, that's all. So to go beyond 1D, we have to go to the inverse scattering series and its diagrams. So the inverse scattering series says you can eliminate internal multiples in any dimension without subsurface information. So that's the next step. Yes. Without any model of how that, in terms of how does the inverse scattering series deal with amplitude period. Yes. Okay, so this is just more of a comment to give you some idea that there, what would a criteria that derives from, let's say, the free surface multiple algorithm itself look like? So, it's just been, what this says is that if you think of the free surface algorithm, it has data that enters, and data times the obliquity times data, and data, we write that data as data basically is some G0, V1, G0. Where V1 is a linear approximation to a perturbation operator. That's an exact equation for V1. It's an exact equation for the linear estimate. And there is no other equation for the linear estimate. The linear estimate states that. So what we're doing here is saying, can we say something in a large set of model types about what this looks like? Is there some property about this that's such that when it enters the free surface algorithm, you can see some characteristic of the series in terms of that data? So what this is saying is, if you have a perturbation operator for the kind of perturbation we've been talking about here, k squared alpha kind of thing, where that's a velocity only varying Earth, no density changing. You get this omega squared over k0. This is not relative change in velocity, but relative change in bulk modulus by Planck. Yes. Then this is what a sandwich of that perturbation would look like in a Fourier sandwich, or some in space, and then you took e to the I k dot r, e to the minus I, p dot r prime omega, and do a sandwich. So you get a k. This is a1, this relative change in, let's say, bulk modulus is a function of space, it's a spatial function, something which is a relative change in properties, this as a function of space. And when you take that Fourier sandwich, you get a difference vector here, or that Fourier sandwich as I described, yes? With a plus, e to the plus and e to the minus. Yes, I'm just explaining what that means. When you get two-parameter acoustic, you get additional terms. This is relative change in bulk modulus. Then this is, let's say, relative change in density. And we know that the density has a gradient in front of it, yes? A gradient operator. Yes? 1 over rho, right? Partial blah, blah. And the gradient becomes, in the Fourier domain, you do a Green's theorem, and you get from one of those plane waves on this side and that side, the gradient on e to the I p dot r brings a p, and then you end up with a dot product. In fact, this is the beginning of your ABO type equation, a cosine. Cosine is here, yes. From a dot product, yes. So, and then if you go to the elastic case, one more, in other words, you add shear, it gives some story like that from the curl, yes. You get gradients and you get curls, okay, running around, and just the perturbation operator. So this is, all this says is this is the perturbation operator in Fourier land. Yes. You have a plane wave sandwich on a perturbation operator. So now, when you take these operators and you evaluate them, in other words, the only difference between V and V1 is a subscript 1. In other words, V, those V's are the actual differential, the actual difference between a reference and an actual differential operator. These 1, 2, 3 just means the first, second, and third parameter. Bulk modulus, density, and shear modulus. It doesn't mean first order or second order. Yes, just 3 parameters. Understood? When we say the linear approximation to be PP, let's say, we would just put 1, 1, 1. It becomes a linear approximation to those quantities. Clear? Linear. This is exactly linear. It's just the portion of, okay. So that's how you get from those to this guy V1. Now in addition, this is not, this V1 that measures data is not just an operator. It's an operator with the G zeros and evaluated on your measurement surface. On your measurement surface, the data. And so what that does is it drives the value of the K vector and the P vector to be the magnitude of the in and out vectors that we call K shot and K geophone, whose magnitude are confined by omega over c. When you have measurements confined to a surface in space, it puts the Fourier conjugate to those variables on a surface as well. In other words, they're restricted, it can't be any value, yes? And so that's what this talk is all about. In other words, it makes those, when you evaluate that V1 on the measurement surface, it takes that K and P and forces this relationship. In other words, the vertical wave number and the horizontal wave number are restricted by their magnitude being omega over c, where omega is the single frequency that you're assuming in this equation. So then the idea is, let's say you have a free surface algorithm. Yes? So this is data without free surface multiples. The first thing here is your data. Data with free surface multiples, yes? And then it takes something like data times data with some operator G. This is the guy that makes it the free surface algorithm. So the point here is that, let's go back to one of those forms with V1. If you take a form like this, and I say that this vector and this vector are going to be restricted to magnitude, their magnitude is omega over c, then this guy becomes some kind of omega over c, omega squared over c squared times cosine of theta. It has an omega squared dependence. That will have an omega squared dependence. This guy is going to have an omega fourth dependence on the measurement surface, so that this omega squared and this will cancel in terms of omega squared. This will cancel with this, and the overall V1 on the measurement surface will go like omega squared. What we're looking for is some kind of property, some kind of property that I can look at in those terms in the series. So, with that argument, this term goes like omega squared, okay? this term will go like omega to the fourth. Understood? Because that's data. In other words, data is looking like omega squared. Yes? So if you have data squared, it's this, again here. So if I take data without free surface multiple and subtract my data, subtract it, this is your data, and then divide by omega squared, yes? And this will have omega squared, omega fourth, and so on. Then if things are work this way, then in the limit, as omega gets small, this minus this divided by omega squared should get small. Yes, because all of them have powers of omega. That is not something I'm advocating you do. That's something I'm saying is an idea where we're looking for a property of the series. What we would do is put some factor in there, A of omega or something, yes? And adjust so that property works. Okay? Am I sure of this property? No. It's an idea, yes? I'm trying to say this is the kind of thing we're going to look at, yes? For not just this, but for the internal. Look at some kind of invariance and then put a parameter that has to search to make that happen on real data. Yes. So that just gives an idea. Yes. Okay. Yeah, there it goes. We're going to be looking at that. Okay, the next talk